Today, we're quickly walking through two closely related problems that matter a lot if you're working with spoken audio or long-form video, turn detection and diarization. They sound similar, but actually serve very different goals for your workflow. Turn detection answers the critical question, has this person finished speaking so I can jump in right now? That's exactly what you want for live voice agents, sophisticated voice assistants, or any system that absolutely needs to reply in real time. Diarization, on the other hand, is all about answering who said what and when did they say it. This is the tool you need when you're transcribing long interviews or trying to pull out every single clip a certain speaker said in a lengthy video. I'll sketch out the core ideas, compare a few common open-source approaches, and then show how a creator-focused tool fits naturally into this entire workflow. Let's start by diving into turn detection first. The truly hard part here isn't just detecting that audio exists. It's figuring out whether the person has actually finished their entire thought or utterance. Pauses can be incredibly deceptive in these scenarios. Someone saying or trailing off with and might take a long, thoughtful pause, and you definitely don't want your assistant to interrupt them mid-thought. Conversely, a short, emphatic "yes, that's right" can be a signal that you absolutely should react to immediately. So the core question becomes how to tell speaker finished with a very high degree of confidence. Most real-time systems begin with a very fast, tiny window classifier called a voice activity detector, or VAD. VADs like Solero or MarbleNet operate on just 20 to 40 millisecond frames and are fantastic at telling speech versus non-speech very quickly. But these basic VADs lack context. They don't see the whole phrase. They only know there is speech here or there is silence. That's the gap where smarter turn detection systems step in to pick up the slack. Projects like SmartTurn build on much bigger audio-to-vector backbones and crucially add in linguistic context. They essentially map complex waveforms into representations that can align with word-level cues, then use a classifier on top to estimate utterance completion. SmartTurn specifically uses a wave-to-vector front-end combined with BERT-like processing. This allows it to pick up on words or tokens that explicitly imply incompleteness, like and, or outputting a probability that the segment is indeed complete. It's a fantastic idea because when decisions hinge on semantics or phrasing, you absolutely need that larger context. The main downside right now is model size and latency, as these models can be quite large and slow to load in low latency settings. In short, very promising accuracy, but they need pruning or smaller architectures before they are ideal for snappy, real-time voice applications unless you have powerful hardware. Now, let's switch gears and talk about diarization. If turn detection asks, is the person finished? Diarization asks the question, which specific speaker is active right now? The typical pipeline for this is quite straightforward. VAD, followed by segmentation, then per-segment embedding, and finally, clustering. The VAD gives you the basic timing for when speech is present. Then, a segmentation model groups those contiguous speech frames into manageable segments. An embedding model converts each of those segments into a unique vector, representing that specific speaker's characteristics. And finally, clustering assigns those vectors to their definitive speaker identities. There are a few different flavors we can use for that crucial segmentation step. The simplest approach is rules-based. You just take short VAD positives and merge them based on predefined silence thresholds. That method is very fast and often good enough for a quick baseline setup. A slightly more advanced method uses a dedicated segmentation neural net, and Pyannote's models are a great example of this. These look at many seconds of audio at once, utilizing bidirectional LSTMs and more context to output overlap labels, meaning multiple speakers are present. That extra context often yields much cleaner segments compared to relying only on VAD and heuristic merging. Once segments are established, the embedding stage generates a unique vector for each one using models like Titanet or a kappa TDNN. These resulting embeddings are then clustered using methods like agglomerative or spectral clustering to decide who is who. This process generally works well when segments are reasonably long and the speakers don't significantly overlap. Short utterances and heavy overlap are precisely where these traditional pipelines start to break down. Short clips just don't have enough speaker signal for reliable identification, and overlap actively confuses both segmentation and clustering. NVIDIA's Nemo toolkit takes a slightly different route in some of its available setups. It uses a faster VAD like MarbleNet and supports multi-scale embeddings, which is a very helpful idea. Multi-scale means computing embeddings across several window sizes, say half a second, 1.5 seconds, 2.5 seconds, and so on, and then combining them. Speech carries information at different temporal scales. So this captures both short, distinctive word-level cues and longer timbral traits. Nemo also features a pairwise neural diarizer. Instead of just clustering, you pass embedding pairs into a small net that predicts presence per frame. This approach can better handle the tricky issue of overlap compared to pure clustering. The pairwise technique scales by averaging those pairwise results for more than 2 speakers, which is quite clever. However, real-world overlap involving many speakers remains a genuinely hard problem in current research. So what does all this technical detail mean for you in a practical sense? If you are just prototyping, start with a VAD and rules-based segmentation to get a solid, fast baseline. Then try using Pyannote if you need better segmentation and you really care about detecting when overlap occurs. Consider Nemo if you want to experiment with that multi-scale idea and the neural refinement for handling messy overlaps. And SmartTurn is fantastic if the key question is, should I reply now? Because it expertly uses linguistic cues. But in every single case, you will run into trade-offs: accuracy versus latency, model size versus device constraints, and the difficulty of handling very short or heavily overlapping speech. Okay, now for the part that creators actually care most about. How do these building blocks help you make short clips from long videos? If you are doing post-production manually, you are essentially doing diarization, plus your own subjective judgment calls by hand. This involves finding the interesting bits, identifying who is talking, finding the perfect in and out points, removing all those ums and awkward pauses, and then formatting them for social media. Frankly, that process takes forever when done manually. That's where a tool like Vizard is intentionally designed to be different. Instead of asking you to stitch together a diarization and turn detection pipeline, Vizard automates the content-side workflow you actually care about. It uses speaker and scene signals to locate those high-value moments, the punchlines, the questions, the emotional peaks, and then auto-edits them into short shareable clips. Critically, it doesn't just spit out raw clips. It gives you a calendar and scheduling engine right there. You can tell it how often you want new posts, and it will automatically queue and publish them for you. Put another way, the open source stacks are excellent for building the algorithmic guts of your system. They help you find who's speaking and where turns happen, and they're great if you need to fine-tune systems for research or a custom pipeline. But they invariably leave you holding the rest: manual selection, trimming, exporting, cross-platform scheduling, and building repeatable content calendars. Vizard bundles the practical elements that creators need every single day into one unified solution. First, it offers auto-editing for viral clips by finding high-potential moments and creating ready-to-post content optimized for various platforms. Second, there's auto-schedule. You set your desired posting cadence, and the AI automatically fills your content calendar for you. Third, you get a centralized content calendar and management system where you can tweak clips and reschedule without bouncing between multiple tools. Compare that to the alternatives. Pyannote is flexible and research-grade, but requires significant integration work and careful tuning. Nemo's multi-scale and pairwise diarizer is powerful for those truly tricky overlap scenarios, but it's heavier to set up initially. SmartTurn is a strong component for making low-latency turn decisions, but its current models are large and need pruning for truly snappy live responses. In essence, those libraries are excellent technological pieces, but Vizard is the creator-facing product that wraps the tech into a hands-off content engine. Here's a practical playbook if you want to start experimenting yourself. Collect representative clips from your content. Make sure to include long monologues, short back-and-forth exchanges, moments with overlapping talk, and plenty of pauses. Run that baseline VAD plus rules segmentation pipeline, and then closely inspect where that basic approach starts to fail. Next, try Pyannote for better segmentation. And if overlap is a real pain point, deploy Nemo into the test. Finally, see what happens when you hand those timestamps and speaker labels into a clip-making tool that scores moments by emotion, loudness, or keyword presence. If you'd rather skip building the entire pipeline yourself, a tool like Vizard will handle a lot of that initial work for you. It lets you focus purely on the final scoring and scheduling, saving you potentially months of trial and error development. One last practical note. None of these methods will magically solve every single issue you encounter. Overlap, very short turns, and idiosyncratic speakers, like those on poor phone quality, remain genuinely tough challenges. The most impactful wins always come from being data-driven. Collect examples reflecting your specific audience, tweak thresholds, and evaluate iteratively. If you are a creator, the single biggest time saver is simply reducing that amount of manual editing time. This is true whether you build a custom pipeline or use a product that manages the entire content loop end-to-end. So the bottom line is this: If you care about when an AI should interrupt someone in real time, look into turn detection models like SmartTurn, but expect to trade latency for context. If you want accurate speaker labels across long recordings, start with VAD and embeddings. Then graduate to Pyannote or Nemo for better handling of overlaps. And if your main goal is turning long videos into a steady stream of polished short clips without building your own infrastructure, tools designed for creators are definitely worth trying. These products bundle the underlying tech with scheduling, calendar management, and automated editing, so you can focus purely on content, not the complexity of the tech stack. If you'd like, I can draft a quick checklist for you to run on some sample recordings to compare Pyannote versus Nemo against your VAD baseline. Or if you'd rather just get straight to publishing, I can lay out a short workflow using Vizard that takes one video and produces a whole week's worth of social posts automatically.